So today we are starting with the second lecture of this lecture series on work, power, energy. I welcome you. So today we will be seeing the energy. So I'll write the heading. So what is energy? Energy is defined as the internal capacity of the body to do work. And this is the only definition which you have to keep in mind while you are seeing the questions of energy. So what is energy and what are the different types of energy? Okay, no need to tell. You have learned the kinetic energy, you have learned the potential energy in your 10th grade. Now you will be seeing in 11th and 12th many energies such as heat energy, thermodynamical energy, electrical energy and various energies. Okay, so these are the different types of energy. You will learn these all energies subsequently in different chapters to come. In this chapter, the work, power, energy, we are concerned with the kinetic energy and the potential energy. Okay, so now we'll see what the different types of energy. But before proceeding to different types of energy, we'll see the Einstein's energy mass equivalence. Okay, so what is energy? Energy is defined as the internal capacity of body to do work. So this is the energy, and this is just definition is enough to define what is energy. Now I've told you there are various forms of energy such as heat energy, electrical energy, potential energy, kinetic energy. Now we'll move on to the next topic, which is the Einstein's energy mass equivalence. Okay. So what is Einstein's energy mass equivalence? You can understand this was given by Einstein. Next is energy mass equivalence. Equivalence means similar or equal to. So here you can see two terms, one is energy and another is mass. So Einstein gave an expression which could equate these two terms, one is energy and one is mass, with a simple expression, that is E is equals to mc square. There has been no any proof to prove this expression, but this expression has been experimentally proven in many of the cases. So we will see what is the expression and which two terms did he equate with this expression. So energy, which is given by E, he equated it to mass and conversion factor was c square. So the final expression for the Einstein's mass energy equivalence I can say is E is equals to mc square. Means I can say that mass can be converted into energy as well as the energy can converted into mass. Okay, like this is earth, okay, and this is sun. So rays from the sun are falling on the earth. You can say that the rays from the sun carry some amount of heat energy in them, and that heat energy falls on our earth, and that heat energy is going to get converted into some amount of mass. So I can say that some amount of mass is going to get deposited on the earth, and this is the reason why we say that the mass of earth is increasing day by day. Okay, so this is the reason I am telling you why is this E is equals to mc square such a very great expression, because it equates energy with mass. Okay, and the conversion factor is c square. Now just let's extrapolate this expression to some new details. So the expression is E is equals to mc square. So tell me, mass is in kgs, c square, which is the speed of the light, it is meter per second square. So I can say that E is equals to kg meter square per second square. So here mass is mass of object and c is the speed of light, which is nothing but 3 into 10 raised to power 8 meters per second. So in this way we have known what is Einstein's energy mass equivalence. Okay, now we will move on to a next topic. So now we'll move on to a next topic, which is kinetic energy. So what is kinetic energy? The definition of kinetic energy is the internal capacity of any object to do work with virtue of its motion. Okay, so this, from the definition you can understand one thing, that this is the energy which is possessed by an object which is in motion, because the definition says by virtue of its motion. So this is the energy which is only present in a body which is in motion. A body which is at rest cannot have any kinetic energy. Okay, so we will see what is kinetic energy. So kinetic energy is defined as internal capacity of any object to do work So this is very important term, motion. This defines that kinetic energy is possessed only by those objects which are in motion, and it is not possessed by all the objects which are at rest. Okay, so the expression of kinetic energy is half mv square. So kinetic energy possessed by any object is equals to half into mass of that object into velocity of that object. Okay, so this is the expression for kinetic energy. This is one form of energy. So the dimensions and the unit will remain same to the energy, whichever it be potential energy, it be any other different energy. Okay, so this is how we have completed one of the most important topics, that is the kinetic energy. Okay, so now we'll see next topic, that is work energy theorem. So now we are going to see a new topic, which is work energy theorem. Before starting this topic, work energy theorem, I must say that this is a very important topic concerned with the NEET examination, because work energy theorem, the questions asked will be mostly solved by this work energy theorem. As well, applications of this theorem will be used in different chapters and its applications are widespread. So learning this topic is a prerequisite to attempting your questions in NEET examination. So let's learn it in a little detail. So I'll write the heading work energy theorem. Okay, so this is the most important theorem, or one of the most important theorem in physics. Okay, so what is work energy theorem? So you can see from the heading work energy theorem, so these three terms. So it's a theorem which expresses work in the form of energy. Okay, or it equates the work done by any object or on any object in the form of kinetic energy. Understanding? So what is the definition of work energy theorem? Work energy theorem says, or work energy theorem is defined as the work done by any object or work done on any object by any force, be it conservative force, be it non-conservative force, be it external force, or be it internal force. Work done by any of these forces on the body is equals to change in kinetic energy of the body. So I can say vice versa, that whatever change in kinetic energy will be there in the body, it will be equals to work done by all the forces which are acting on the body in its journey. Okay, so this is the definition of work energy theorem, and it encompasses all the works, be it conservative energy, be it non-conservative energy, be it external energy, external force, or any internal force. So each and every force will be encompassed in this theorem, and this makes it more special. So what does work energy theorem say? Work energy theorem say work done by all the forces. So all the forces means they can be conservative force, they can be non-conservative force, they can be external force, or it can be any internal force. Work done by all these forces will equate to the change in kinetic energy of the body. So work done by all the forces, which can be conservative, non-conservative, external and internal, can be equals to So this is the expression, this is the definition of work energy theorem. Now we'll go in a little detail and we'll express it mathematically. So work total acting on any body can be equals to work done by all the forces, or I can write work done by all forces. And I know these forces can be conservative force, non-conservative force, external force and internal forces. So I can write work done by all forces means work done by conservative force plus work done by non-conservative force plus work done by external force plus work done by internal force. So this is work done by all the forces, which we represent this way, is equals to change in kinetic energy, change in kinetic energy of the body. So I can write this change in kinetic energy of the body as K final, Ke final, kinetic energy final minus kinetic energy initial, which will be equals to work done by all forces. So this is the final equation of work energy theorem. So I hope you have understood the work energy theorem. So again, work energy theorem says that work done by all the forces, which can be conservative force, non-conservative forces, external forces and internal forces. So work done by all these forces will equals to change in kinetic energy, which is kinetic energy final minus kinetic energy initial. So in this way we have completed the work energy theorem. Now we will move to the next topic, that is how to use this work energy theorem and how to solve problems based upon work energy theorem. So now we are starting how to use work energy theorem in different questions and numerical problems. Okay, so we will write how to apply work energy theorem. So how to apply work energy theorem? So the answer to this lies in some few steps which I will be telling. You have to apply these all steps to your questions, and I hope that your questions will not be wrong. So first is assign final and initial positions of the body. Okay, so assign final as well as initial positions of the body. What does it mean? Suppose I am just releasing a ball from some height. So the height from which I am releasing the ball will be the position initial. Okay, and the last position of the ball will be the ground, because it is going to touch the ground. So in this journey from ball, from top, from the point where I am releasing to the bottom, that is the ground, so I'll assign initial position as the point from where I am releasing the ball, and final position will be the position where ball touches the ground. So this is how we assign final and initial positions to the object. Okay, so this is the step number 1. Now second step is draw a free body diagram of the object So the next point is, draw a free body diagram of object when the body is passing between initial and final positions. What does this point means? Suppose this is a ball and I am dropping this ball from certain height. So the ball is dropped, this is the first position or initial position. Next, the ball will go down and ball will then touch the ground, which is nothing but the final position. Between these two positions, the ball will perform a journey, a vertical journey. So I want you to just pause this journey for a second. So you can pause this journey anywhere between the ball releasing of the ball and just ball touches the ground. So between these two, suppose if the ball is in middle, I want you to capture that movement and draw an FBD. Okay, so what does FBD means? FBD means free body diagram. Free body diagram is a diagram in which you denote all the forces which are acting on the body. Okay, so how we'll draw a free body diagram? Suppose now the ball is falling. Now a ball which is falling, how many forces act on the ball? In ideal conditions, the forces can be the gravitational force, but in some non-ideal conditions there is also a air drag. So additional force which can be a air drag force, and simultaneously the work done by this air drag force will account into matter. So the next point is, draw a free body diagram of an object when the body is passing between the initial and final positions. Now we'll write a third point. Third point says, find the initial and final positions of the body. Okay, so how will you find the initial and final position of a body? For this you'll require initial and final velocities. So you have to see what is the initial velocity when we have dropped the ball. That will be equals to 0 in that specific case. But if there is suppose another case, you have to find the initial velocity and find subsequently the kinetic energy. So this will be your initial kinetic energy. Suppose now the ball is on reaching the ground, has some velocity, so that is the final velocity, and that kinetic energy will be called as the final kinetic energy. This way you will get two different kinetic energies, the kinetic energy initial and the kinetic energy final. When you will subtract this, you will get change in kinetic energy, which will be equals to work done by all the forces which you can depict or which you can denote in the free body diagram. Okay, so these three are the most important steps in the work energy theorem, and these three steps are sufficient to make you solve questions on different types of work energy theorem. So now let's take an example which will clarify your concepts of work energy theorem. So now we'll take an example which you have seen earlier. I have a ball. I am dropping that ball from a certain height h. Okay, this is a ball. So this is the ball and I am dropping it from a height h. Okay, so this is the ground. Now I am dropping the ball from height h. So tell me, now we'll go to the first point. What is first point says? Assign the initial and final positions of the object. So our object is the ball and its initial position is this. So this is the position 1 or initial position. Now we have to assign the final position. The body reaches at this point on the ground and this is called as the position number 2 or final position. Now what is the next step? Next step is draw a free body diagram of that object when it is passing between the initial and the final positions. So suppose if this is the journey, I take any point and I draw this body, and now I am going to draw the free body diagram of this body at that particular instant. So now tell me, what are the different types of work, different types of forces which you are going to see in this free body diagram. So first will be gravitational energy. Okay, so this is the gravitational force. So is there any other force? Yes. In non-ideal conditions there will be other force which is called as the resistive force. So in this particular case I can see only two forces. One is the gravitational force and the second is the resistive force. So I'll write the third point. Okay, suppose at this position, now what does the third point says? Third point says that draw or find out the initial and final kinetic energies. So where will I get the initial kinetic energy? At the initial position. Where will I get the final kinetic energy? At the final position. So I have to find the initial kinetic energy. So initial kinetic energy, initial is equals to half mv square. So this I'll write as Vi. Here the kinetic energy final will be half mv final square. So this is how I have written all the 3 points. Now what is the fourth point which I haven't told, but it's not that important to be told. The third point is, now you can equate the work done by all the forces which you can see in this free body diagram equals to the change in the kinetic energy, that is Ke final minus Ke initial. Okay. So if I rub this diagram, now I know that work done by all the forces, all forces is equals to work done by gravitational force plus work done by resistive force is equals to change in kinetic energy, which is half mv initial square minus half mv final square. So this is the most important expression which we have got in this particular expression. So this is how we are going to see, or we are going to solve the problems, numerical problems or work energy theorem. It is very simple. Whenever there is a numerical, just put work energy theorem into that particular question. You have to just solve it with these 3 important steps and you will get your answer. So in this way we have covered the work energy theorem and how to apply this work energy theorem.